So our next speaker is Seiji Yunoki from RIKEN. So a bit of a brief introduction. Yunoki-san graduated from Applied Physics in 1996 from the Division of Engineering in Nagoya University. And Yunoki-san is Chief Scientist in the Computational Condensed Matter Physics Laboratory at RIKEN since 2017.
はい。で、これがで時間があれ時間どこなんですか。Okay, thank you very much for the nice, kind introduction. I would like to start by thanking the organizers for organizing this very special workshop. So what I was planning to give in this talk originally was about quantum classical data transformation using classical computers. But after knowing what exactly this workshop is all about, I decided to change the content a little bit. And I would like to spend a little bit more than half of my time to explain what is going on in RIKEN and what the RIKEN is what the RIKEN is planning to do with quantum plus classical computing. Okay, let me see. So, of course, the RIKEN is the largest national institute for basic science in wide range of research field, and the main campus is located at Wako, just outside Tokyo, and we have just launched new research institute for quantum information and quantum computing, RIKEN Center for Quantum Computing. The director of this research institute is Yasu Nakamura, and for instance, his team has been developing quantum computers based on superconducting qubits, and his quantum computers will be the first domestic quantum computers built in Japan, and this is scheduled to be released within this academic year. And of course, we have also a research center for classical computing, HPC, and this center is like RIKEN Center for Computational Science, directed by Satoshi Matsuoka. And here we have a supercomputer Fugaku, which was the fastest supercomputer around the world in 2020 and 2021. And last month it was announced that this Fugaku is still the second fastest supercomputer, and also is ranked in the first place for different metrics. And having received this ranking, we have released a press release in December 15, and since this press release is only in Japanese, I just translate it in English. So the title of this press release is like results of the world ranking of the supercomputer Fugaku and RIKEN's future response continued to maintain the world's top position. And in this press release, it's clearly stated that the RIKEN will strengthen its research and development of quantum classical hybrid computing, which combines supercomputer with quantum computer to perform advanced computations. And as a response to this comment, the director of RCCS, Professor Matsuoka, made the following comment: RCCS will use our experience to integrate with new computational paradigms such as quantum computing, quantum computation, and to explore new supercomputer configurations for the next generation of high-performance computing. So I wanted to show this press release because it clearly shows the RIKEN's strong commitment on the quantum classical hybrid computing in its future direction. Okay, under a very strong leadership of Professor Gonokami, he is the new president of RIKEN. He initiated, so he launched a new initiatives called Transformative Research Innovation Platforms of RIKEN Platforms. TRIP in short, and here, essentially we develop quantum classical hybrid computing, and we use it for research. And in this project, there are three main streams. Trip one is like high quality data acquisition. Here, since RIKEN has a lot of high quality data, so that we can use this wisely for research in Japan and probably around the world. And trip two is about AI cross mathematics. Here we would like to develop quantum classical hybrid algorithms and apply them to quantum computational science. Trip three, here we would like to develop quantum classical hybrid computing systems and environments. And in trip two, we have organized this RIKEN Quantum, where all researchers in different research fields across the different research centers in RIKEN come together to promote quantum computational science for basic research. And just at the beginning of this week, we just put this advertisement to hire 10 postdocs, research scientists, or senior research scientists for this project to begin with. Okay, so in RCCS, we've been developing quantum computing simulations for HPC machines like Fugaku. Here, of course, the good quantum computing simulations are essential to develop a good applications of quantum classical hybrid computing, and also state-of-the-art quantum computing simulations are necessary to explore what the limit of the classical computation is. And Ito-san and his collaborators has been developing faithful quantum computing simulations based on state vector method for more than 15 years, and they have achieved world largest simulations for 45 qubits using K-computer in 2019, and they are planning to make another world record to simulate 48 qubits using Fugaku probably next year. And we are expecting that the maximum number that we can simulate using classical computer is around 50 qubit, which more or less sets the limit of classical computation. And also we are developing another quantum computing simulations based on tensor network, especially MPS, because MPS is very suitable for parallel computation classically. And here is the benchmark using Fugaku in weak scaling. So we increase the number of nodes proportionally with increase the number of qubits. And you can see that we obtain a perfect scaling here. And at the same time, we develop also a tensor library to manipulate tensor operation very effectively, and owing to this, MPS is better, can have a better performance than one of the well-known open software tensor. Okay, so in RIKEN also there are quite a lot of researchers already involving to develop quantum algorithms and application for simulating quantum many-body systems, simply because we have a lot of good scientist with strong background of quantum n-body systems in condensed matter physics, elementary physics, nuclear physics, and quantum chemistry. Therefore, we know exactly what the problem that we can solve, and this is exactly where the quantum computers should be applying. So this is the list of paper on quantum algorithms and the related subjects that we published. I mean, in our group, and not including the papers by other groups. And I would also like to spend additional minute to highlight some of our works colored by blue. No, yeah. So in this project, we propose to implement symmetry in the VQE scheme, because our Hamiltonian is very often have symmetry, such as translation symmetry, point group symmetry, and SU2 symmetry. And the idea is very simple, simply because we use this projection operator to restore the symmetry of the Hamiltonian, since the parameterized quantum circuit necessarily breaks the symmetry of the Hamiltonian. The problem here is that this projection operator is not a unitary operator, but this translational operator, for instance, is a unitary. And therefore, we can take advantage of quantum classical hybrid scheme and use quantum computer to evaluate this translational symmetry operation, and the rest of this summation can be treated classically as post-process. And by doing numerical simulation, we found that including the symmetry, the convergence to the ground state is much faster. And we also use one of the IBM's quantum devices to solve four-side Heisenberg model. And there we obtained essentially exact result. And this should be in sharp contrast with one of the earliest report by IBM, where they have having a difficulty in getting to the ground state using the efficient parameterization. But of course, now everyone can do much better. Okay. So one of the problem in VQE scheme is we don't know generally what the right circuit structure would be for the particular problem that we want to solve. And here we propose to use a quantum adiabatic process to construct a better circuit structure for the model that you want to solve. And for the quantum adiabatic theorem, one can construct a quantum circuit that guarantees to converge the ground state. And this is essentially the similar idea of QAOA. And by numerical simulation, we show that indeed the quantum circuit constructed by discretized version of quantum adiabatic process can have a best circuit with the shortest number of layers of gates set by Lieb-Robinson bound. And here, in condensed matter physics and quantum chemistry, the good wave function was just a factor. The very good variational wave function for the correlated electron systems. And here we propose how we can implement this Gutzwiller factor in a quantum computer. And the problem here is that the Gutzwiller factor, or just a factor as well, is not a unitary operator here. So the question is how we can introduce this in the quantum computer. Here our idea is very simple. To use discrete Hubbard-Stoyanovich transformation to decompose this 2-qubit non-unitary operator into a product of two single-qubit unitary operator at the expense of introducing the additional classical Ising spins. And now we can treat these single qubit unitary operators in the classical quantum computer, and this summation, classical summation, can be treated in classical computers. This is a very similar idea of circuit cutting or entanglement forging. And we used the IBM quantum device to simulate a two-side Hubbard model with good wave function, and we obtained a very much reasonable results. Okay, so in addition to the ground state and the excited states, we are also very much interested in thermodynamic properties. And here we propose how we can do a calculation, thermodynamic calculation, using quantum computers, especially microcanonical ensembles. And the point here is we introduced this microcanonical thermal pure quantum state defined by this wave function, where G of E is this Gaussian function, H is Hamiltonian, and E is target energy. Remember that the microcanonical ensemble energy is given. And phi here is a quantum random state. And one can show that using this function G, everything like the density of state, thermal entropy, and inverse temperature can be evaluated from this function G. And again, the question is, okay, so the difficulty is this non-unitary Gaussian operator. So how we can implement this to the quantum computer is simply by using Fourier transform of G. So essentially this G function can be obtained by Fourier transform of time evolution operator, which is unitary, and therefore we can calculate these two quantities in quantum computer. And this integration can be treated classically. And of course, realizing this random number in quantum computer is very tricky. However, we found that random state generated by single qubit and two qubit random gates is enough for our purpose. So this is so here we propose the weight adjustable quantum loop gas circuit state for the ground state of the toric cord with external magnetic field on the square lattice. So very recently, Google team proposed in science paper a very nice idea to generate a ground state of the toric cord on the square lattice by using Hadamard gate and the nearest neighbor CNOT gates. And here we borrowed the idea to construct a weight adjustable quantum loop gas circuit state defined in this wave function. When you set theta equal to pi half, this becomes the exact ground state of the toric cord on the square without magnetic field. And here, this wave function can be also constructed very much the similar way that the Google team did, simply by replacing Hadamard gate with the rotation Y gate. And here we show that indeed this wave function is a very good wave function for the toric cord with magnetic field with any strings. And we would love to use one of IBM quantum devices to implement this state of a toric cord on the honeycomb lattice. Although the device topology is a heavy honeycomb. So I just briefly I will briefly mention the main subject of this talk. So this is about this encoding of quantum state by quantum circuit for quantum classical data transformation. It's always a problem. To implement a classical data into a quantum state. And there are several ways. Representing a classical data with a quantum state is not a difficult part, because there are many ways to do that. And these are the two most popular ways to encoding the quantum, the classical, to representing a classical data with quantum state. And the difficult part is how to implement this quantum state in a quantum circuit form. So of course, mathematically, this can be done, provided that if you use exponentially large number of qubits. And here we propose a very approximate way to do this task. And it turns out that this can be done very not easy, but very properly based on the technique used in the tensor network method. So I just skip this, and this work can work, for instance, for the classical data. So here is one of the examples that we did numerically. Here is the classical data, and this is the reconstructed classical data represented by a quantum circuit state. You can see that by increasing the number of unitary operators, one can actually reproduce a classical data reasonably. And we have also a better way to do this with less qubits. Okay, so I will stop here. Yeah, thank you. Thank you very much.
Thank you very much for the great talk and all the projects that you guys are conducting at RIKEN. Is there any question for Yunoki-san? I do have one question. So when you show the state vector simulator and the number of qubits that you can reproduce, how far can you get if you introduce noise? I guess that the results that you showed were for ideal systems, right?
Maybe one qubit less.
Okay. And when you were talking about the matrix product state simulator and the performance of the simulator being better than iTensor, what did you use exact contraction techniques for the matrix product state or approximate contraction techniques? How did you get a better performance than other?
It's not the exact contraction.
So you are using approximate contraction. Okay. Thank you. Any questions? All right. So if there are no more questions, let's thank the speaker again.